lecture 2. Today we will talk about some special cases of discrete random variables. In the previous lesson we talked about the concepts of random variable, discrete random variable, and probability distribution. In probability and in theory, we typically try to generalize the random variables that we study. We try to classify them in a very general way. And that is also the case for discrete random variables. So sometimes we say, oh, that variable, that random variable is a Poisson variable, or it's a geometric variable, or a binomial variable. And what we are saying is that the way that we calculate the probability distribution is the same for all those variables, even though they might be very different experiments and very different variables of interest. And that's what we are going to study today. We are going to study how these variables can be computed and how we can study them and explore them. We will also talk about how we can calculate some basic statistics from discrete random variables, such as the expected value, or the variance, or the standard deviation. So let's start by the Bernoulli distribution. A Bernoulli random variable is a variable that can only take two values, either 0 or 1, or any other kind of values that you can imagine, but typically just 0 or 1. Or we also sometimes say that it can either take success, the value of success, or the value of failure. The probability max function of a Bernoulli, it's always the same. You always calculate the probability of the random variable having a certain value, either 0 or 1, using a function that is similar to this one. The probability mass function of a Bernoulli is quite intuitive. So you have the probability of being 1 being, for instance, p, and the probability of being 0 being 1 minus p. Everything else is just 0. So in order to define a Bernoulli random variable, we typically define the p, the probability of the occurrence of the value 1. So examples: the toss of a coin, the flip of a coin, it has two outcomes. One outcome has a probability of p, the other outcome has a probability of 1 minus p. The doing of an exam, I either pass or I either fail. So if I pass, I have success, so it has a probability of p. If I fail, it has another probability, 1 minus p. The inspection of a light bulb or any other type of equipment, it either the test either passes or fails, so 1 or 0. Another example: a child is born, it is either a female or a male, so either one case or the other. So every time you have two cases and you have a probability for one and the other is 1 minus the probability of the other, because of course only one of the two events can occur, you say that the random variable is a Bernoulli. The geometric random variable is a little bit more tricky. It has to do with the number of flips that you have to do in order to get a success. So it has to do with more than one trial. So you repeat the random experiment until you get a case of a success. So in this case, the range is 1 in case I get the success in the first trial, 2 if I get in the second trial, 3, and so on and so forth. So how do I calculate the probability max function, or the probability that a random variable assumes a certain value? Well, it's the probability of success multiplied by the probability of non-success, 1 minus p, elevated to the power of k minus 1. But we may also be interested in a random variable that estimates the number of successes for a given number of trials, for a given random experiment. So in this case, consider that I have n trials in my random experiment. The range of x in this case is 0, because I may not even see one case of success. 1, 2, 3, until n cases of success, if in all my trials I see successes. So the probability of the random variable assuming the value key equals the probability of success elevated to the power of key multiplied by the probability of failure 1 minus p elevated to n minus key multiplied by all the combinations of having key successes in n cases. And we also have a very useful distribution, which is the Poisson distribution. Finally, we have two very important concepts: the concept of expected value variance, which is also related to standard deviation. When you try to estimate the expected value of a random variable, what you are trying to do is kind of an average of the values that may come out with the probabilities that they will that they are associated with. So you're kind of like using a balance. You're kind of like putting the probabilities as the weights multiplied by the values that the random value will take. Because you want to know, in general, if I only had one number, what would come out, even if that number is not in the range of the random variable. So for instance, if you had these three probabilities for these three values, you would calculate the expected value in this way. The variance in turn is a measure of the dispersion around the mean, around the expected value. So you always compute it like this. First you estimate the expected value. Then you apply the formula to calculate the variance. And the standard deviation is just the square root of the variance. So by the end of this lesson, you should be able to identify and differentiate popular discrete random variables and their associated distributions. And we should also be able to calculate the expected value, the variance, and the standard deviation of any kind of discrete random variable. So, thank you again for watching, and see you next lesson.